What's up, my dudes? I gotta turn the lights off so I get the full effect. Yeah, much better, but you can't see anything different, but that's all right. It's all right. I should have a title page to this. Um, should I? I don't know. Maybe I shouldn't. But we are going to, by the end of this, talk about orbital motion. Maybe call it orbital mechanics. I don't know. Um, but yeah. So if you remember, let's go back a few. Oh boy, let's go back a few. Wait. Go back to slide 1. Yeah, right. We want to talk about this question. How fast does the space shuttle have to move in order? Wait. Oh yeah. There was this thing called the space shuttle that looked like that. And you know what the space shuttle is, but people in years to come will not have known what the space shuttle is. Maybe. Wow, I digress. The question is, how fast does the space shuttle go? You should prove to yourself that this expression here, v is the square root of gr, is the expression for how fast the thing has to move in order to stay in orbit at a radius r, or in orbit with a radius r. But if you remember, we said, but g is not 9.8 because it's 9.8, quote, near the surface of the Earth. All right? Well, let's talk about why it's 9.8 near the surface of the Earth and what it is in other places. All right? So we can calculate the strength of G. Well, yeah, we can. Because G, the only place we've seen, we've put it in kinematics equations, but in terms of force, we've said that, well, if we say, here's a big deal, your weight that we've called Fw, well, yeah, we call it W, is a gravitational force, right? Between you and Earth. It's the gravitational force that the Earth exerts on you. Yeah? All right. So we've written that as mu times g. But what we're saying is that is a gravitational force between you and the Earth. Well, gravitational forces go as G, M, U, M, Earth, and the separation between you and the Earth. Well, remember, we have to qualify that. That separation is between your center and the Earth's center. All right? Here's the Earth. There's you. Where? Doesn't matter. You can't see yourself. You're too small. How far are you from the Earth? Again, how far are you from the Earth's center? Well, you're that far plus how far it is to your center from there. So it's 6 million plus meters. Well, let's write it as this. 10 to the 6th meters, really closer to 10 to the 7th meters, plus another meter or so. So it's, you know, it's 10 million and 1. Let's just call it 10 million. Or really what we're saying is, let's just call it the radius of Earth squared. That's how far you are from the center of the Earth, the radius of the Earth. Fair enough? I'm just going to move this stuff over here. And I should really write this as G Earth. Well, notice what goes away. And we have an expression now for G of the Earth. Big G, mass of the Earth, divided by the square of the Earth's radius, which we can generalize and say G on any planet is G times the mass of the planet over the square of the planet's radius. What y'all ought to try is make sure you can get, well, this better darn well come out to 9.8 or 9.81 or whatever you want to call it. You better darn well be able to get that, plugging these numbers, right, mass and radius, into that expression. Or into this expression, same expression. All right, and then pick another planet. Pick your favorite planet. Who doesn't have a favorite planet? The sun's not a planet. I know, neither's the moon. And Pluto, I don't even know. Uh, find one. Find another G. Okay? Okay. Good. Now, yeah, blah, blah, blah. G is 9.81, right? Or 9.8, sure. We've qualified that. So now we can find G on the surface of another planet if these planets have surfaces. But this one's a gas planet. It doesn't have a surface. You know what I'm talking about. So, but what about G anywhere else near Earth? It's not, quote, near the Earth's surface. Or what about near any other planet that's not on the planet's surface? Well, what we can say is, even if here's Earth, and I forget Earth, let's just call it planet, and here's mass M, it's located some distance r from the center of that planet. Well, there's a force that acts on this. Oh, I'm sorry. And you know what? No, we don't even have to say it's in orbit. This thing's just sitting there. I don't know. Is that possible? No, it's not really it's not really possible. It's fine. So, but there's a force, let's just say. How well can you see the blue? Sometimes I've heard not very well. But there's a gravitational force that acts on that mass. All right? The strength of that force, well, is really mg. It's the object's weight, even when it's way out there. Right? If we took you out into space, you'd still have the same mass you have, but you wouldn't weigh the same as you do here on the surface of the Earth. But we can still write that weight as mg, whatever g is out there. So again, Fg is still g, mass of the planet, times whatever mass this is, divided by how far apart they are, and that's equal to m, right, whatever mass this thing is, times g at that location. So, maybe this is obvious from the last page, maybe it's not. If you are not on the planet's surface, but some distance r from the planet's center, well, there's an expression for g. G, mass of the planet or object or whatever it is, divided by r squared. R squared. People have a tough time remembering which of these masses goes away. Well, remember, this thing is the thing that the gravitational force is being exerted on. Well, I shouldn't say that, because there is, of course, a gravitational force exerted by, experienced by this one, but the reason we're talking about this is we want to say, well, what if this thing is in an orbit around that planet that's a circular orbit? All right, so this is the thing moving in a circle. It's the thing that, has the acceleration that we're concerned about, the thing that's, moving in a circle. Okay, that's an expression for g at any location, well, really at any location, in this case, not on the surface of a planet, but at some distance r from its center. That's okay? That's okay. Now, finally means it hasn't taken that long, but here's our space shuttle moving in a nice circular orbit. Will it keep going? Oh, yes. How sick is that? Go, go, go. Oh, come here. Yeah, good. Ooh, it's not bad. Oh, yeah, good. Here's our circular orbit. Space shuttle's moving in this, stop already. There you go. In this circular orbit, and we want to know how fast it goes. Well, I know we came up with an expression earlier, but let's just kind of start back from the beginning. This thing moves in a circle. Therefore, there is a force that has to point inward, really a net force that points inward. In this case, let's say, there are other masses in the universe, of course, that are all pulling on this thing, but the predominant force is this force that the Earth exerts, we'll call Fg. Right? We say that Fg is mv squared over r. Let me back up and say that the centripetal force which is MAC, well, the centripetal force, the only one there's not an outward force in this case. The only force is this gravitational force that provides the centripetal force. Well, how do we write FG? Sure, we say it's the mass of the space shuttle times G is mv squared over r, right? And we can get rid of this. Oh yeah, it's still shuttle. Get rid of that, right? That gives us our v is gr. Sure. But wait a minute, we don't know what g is out there. So what we say is, well, instead of just writing this as mg, let's write it as gravitational force, g, mass of the Earth, mass of the space shuttle, divided by the square of this radius from here to there. There's r. Now that equals m shuttle v squared over r. M shuttle goes away. And the speed, let's see, oh, also we can get rid of, let's see, we've got an r here and two factors of r there, so the squared goes. And notice what we get. We get v is the square root of g m e over r. Okay? So kind of neat, this says, well, the farther you are away from the Earth, the slower you have to go. Which seems kind of strange. But if you think about planets, right? Think about the sun. Here's the sun. Here's Mercury, Venus, Earth, Mars, whatever's next. Venus, Mercury, Venus, Earth, Mars, Jupiter, Saturn, right? The farther away those planets are from the sun, the longer their orbital periods, the longer their years. All right? And here's why. Now, this is an approximation because what you might know about planetary orbits is that they're not circles. They're ellipses. So this works for circular orbits, and Johannes Kepler had a heck of a time in figuring out all that stuff that has to do with planetary orbits not being circles. Boy, did it give those early astronomers headaches. But things just didn't work out with circular motion. Golly, there was a lot of good math and calculus and physics that could be applied to all the data people had collected, but geez, if it just didn't work out until Kepler said, you know why? Because they're ellipses, and then everything worked out. Anyway, we will only do circular orbits, right? And the orbit that a space shuttle flies through, can you say it's perfectly circular? I don't know that, but I think it's well, it's certainly close enough for our purposes. Okay, so be able to, I don't know, don't memorize this, but be able to do this. Be able to get to this expression, right? GMM over r squared is mv squared over r. And then you solve for the thing you want to know. All right, I'll tell you everything except for the one thing. You find that one thing. All right, awesome physics. I feel like there's a really good question to ask. A puzzler, a stumper, but I'll think of it. There's your orbital stuff, folks. Great physics. Just awesome. See ya.